the amount of combustion. Everything else stays the same, still 50% load, but the damper control on the fan goes wacky, and we're putting in more air than we should. Okay, so that will increase, typically will increase the flue gas exhaust temperature. And so here's what's going on. Heat transfer in the combustion zone is dominated by radiation. It's so hot. Remember, radiation is what? T high to the fourth minus, say, T2 to the fourth power relationship. And that 3,000 degree fireball temperature is so high that the T to the fourth, when you do that math and subtract, is such a big number that the radiant heat transfer is really large. So we say roughly 75%, you know, if you got a swaggy number, I mean, it depends, but the dominant mechanism for transferring heat inside that furnace area is radiation. So the flame zone temperature is an important factor. So then we say heat transfer is proportional to the fourth power difference between the flame temperature and the tube wall temperature. So a very small change in flame temperature will significantly reduce the heat transfer in the combustion zone. So if I put in this larger amount of air, I quench that flame temperature. I cool down the fireball a little bit, and that really knocks that T to the fourth temperature difference down. I transfer less heat by radiation. The convection can't make up for it, so that energy stays in the gases and goes up the stack. So you see an increase in flue gas temperature. More or less.
More or less, the boiler is running lean, kind of like an engine running lean.
Yes. Yeah, leaner than it should. Because lean is relative to fuel, right? More air, less fuel. Yes, that's correct. Yeah. Yeah, there you go. Okay, the most common factors influencing flue gas temperature, and this just summarizes what we've been through. So I'm not going to read back through those for you again. Okay, so the temperature loss management summary. So this is what we need to consider. Monitor and record flue gas temperature with respect to boiler load, ambient temperature, and flue gas oxygen content. Okay, so, well, we'll get into that. Compare flue gas temperature to previous similar operating conditions. But you got to get the parameters, the ambient temperature, the load, and the flue gas oxygen content to have been in a similar range to do a fair comparison. Maintain appropriate fireside cleaning, maintain appropriate water chemistry, and evaluate heat recovery component savings potential. And we will get into that. We'll use the measure tool to do that for us. Okay, combustion component. Okay, so stoichiometric combustion. Let's burn a little methane here. A little CH4, a couple of O2s. We're going to do it right. We get CO2 and 2 H2Os plus energy. Okay, that's doing it right. We don't have any of those COs over there. So in a perfect world, we would get perfect mixing. So every place you had a methane molecule, you would have an O2 or 2 O2 molecules right there, and they would just do that little combustion thing, and life would be perfect. Problem is, we just don't get perfect mixing in the real world, okay? But So for stoichiometric combustion, theoretical air, because right, the amount of air that we provide for stoichiometric is called theoretical, and that's because we get perfect mixing. One molecule, just the right amount of oxygen, same thing here, all over the entire combustion zone. It's perfect. Actual combustion, not quite so nice, okay? So we still have our methane, we still have our two O2s, but we get some CO2 and we get some H2O. Now, what's this CO doing over here? That's not good. I don't want him. What, an H2? You mean some of my fuel didn't burn? What, a methane molecule? He couldn't find any oxygen. And then I got some spare oxygen that was over on the other side. It was too far away, and that H and that methane molecule just couldn't combust. So they're going up the stack hot. So unreacted methane. CO, you can burn CO. It's not a good fuel, but you can burn it. And hydrogen are fuels resulting from incomplete combustion. Okay, so that's not good. You can have safety, health, and efficiency issues. Safety, they can burn in the stack where you don't want them to burn. They're still fuels. You get the right mixture, you can have a fire in the stack. Health, you don't want to put that stuff out. People breathe it. And efficiency. So combustion management strives to eliminate unreacted fuel. And how do we do that? We start cramming more oxygen in. Because we know we're not going to get perfect mixing, so we got to have more oxygens floating around so that we can burn everything effective. Okay? Excess O2 provided to the combustion zone essentially eliminates unreacted fuel. So we're going to keep cramming in more and more oxygen until we burn all of the stuff appropriately. So there's all the carbon will burn to CO2, all the hydrogen will burn to water vapor, and we won't have anything else combustible left. So that's combustion. These combustion management principles in here are pretty simple in this course. Put in all the air you need until you burn all of the fuel. That's pretty simple. Okay, combustion management principle number 2, but don't put in any more extra than you absolutely need. So be careful on how much you add. Okay, because extra oxygen added to ensure a complete reaction of the fuel is heated by fuel from ambient temperature to the temperature of the exhaust gas, and then it goes up the stack. Well, where do we get the oxygen that we burn? Well, we can't afford bottled. You know, you could buy bottled oxygen and you would be much more efficient, but you can't afford it because it's free, right? It's in the air. So that's what we use. So in other words, to get 1 mole of oxygen, we have to bring in 4.76 moles of air. And 3.76 moles of them are basically nitrogen and trace gases. And you get some water vapor too, but that, you know, that's a separate accounting. We usually think about this as dry air coming in. So think about it. So in that equation, I need 2 O2s, so I've got 2 times 3.76, and that's called N2. In the utility industry, instead of just talking about nitrogen, they talk about atmospheric nitrogen. They talk about N2A. If you see N2A, that takes all of the dry gases except oxygen and just kind of lumps them together. You know, so it's not really just all nitrogen. There's a little bit of argon. There's a little bit of CO2. There's probably a trace of CO. I mean, whatever else is in there besides the water vapor is called atmospheric nitrogen. You'll see that term sometimes. I think I have it in these slides someplace. If you see N2A, it's atmospheric. And it has a slightly different molecular weight than straight nitrogen. Straight nitrogen is 28.1 something. And N2A is, I don't know, it's a tenth different, because it's a weight average of all of the different gases that make it up, okay? But anyway, so we're bringing in all that nitrogen and gases cold, and we're putting them up hot. Fact of life. Okay, so minimum oxygen evaluation. Minimum oxygen limits can be determined by measuring combustibles, okay? So what will happen, so the way we measure the excess O2 is we just put a probe in those flue gases, and we pull a sample, and that sample will tell us what percent on a volume basis coming through there is oxygen. So, you know, if you were stoichiometric combustion, your perfect theoretical air, how much oxygen is left in the flue gas? Well, none, because we burned it all up. That's what stoichiometric combustion is. But we can't do that. We have to put in some extra. So the amount that doesn't react in the combusting of the fuel is left in the flue gas, and we measure that with a combustion analyzer. And so it'll tell us. So you see flue gas oxygen percent down on the bottom. And then you see combustibles. Well, if I have too little excess, I'm not putting in enough, I guess I'm burning rich, because I got more fuel and I don't have enough air to burn it. And so my combustibles go through the roof. Look at the parts per million. At 1%, I'm about 60 parts per million. And if I start going down less air than that, it is just going almost asymptotic, going up like crazy. As I come down to 2%, I'm down to 20, down to 3%, I'm down to someplace around 10, and then it pretty much levels off till I get to 7. And when I go to 8, it's starting to come up again. And then I've got so much air blowing around in there, it's starting to be detrimental to being able to burn anything. You know, velocities are too high. It's just, there's not enough time at temperature. I start to not be able to burn it because I have so much air. So someplace in there is kind of a sweet spot where I want to operate. Okay, so here's another example, fuel rich, air rich. And you see, so notice we've got, on this one, we got the red graph, which now they've added CO and combustibles. So, I mean, what's happening is as we cut air back enough, then we don't even have enough oxygen around some of the carbon molecules to burn them to CO2. They start burning to CO, which is not good, okay? And then as I put in more and more and more, the CO and combustibles go down, but NOx goes up, efficiency goes down, because I'm just blowing so much air through there. And so you see the efficiency is peaking someplace, you know, it depends on the system, 2, 3, 4, 5%, okay? And so I still have a little bit of CO, you know. I could have less CO, but then I have to put in more and more air, and I've got more and more nitrogen going through the system, and I start carrying away more and more heat. So I don't want to go further that way. I can't go less than the ideal, because then I start gaining in CO and combustibles. So there's kind of a sweet spot in there, someplace probably between 2 and 5%, depending on the system. Okay. Babcock and Wilcox a long time ago, for proper combustion, three factors dominate the combustion process. They call these the 3 T's of combustion. And you got to get these right to have good combustion. You got to have time, temperature, and turbulence. Time at temperature for the combustion, for the oxidation reaction to complete. It takes time. It's not instantaneous. Reaction temperature, you got to be above that combustion threshold. So you've got to have that fuel and oxygen together for enough time at enough temperature, and then for it to oxidize. And then we have to have good mixing. We have to have turbulence to keep all of that stuff mixed up so that I have oxygens in close proximity to fuel molecules so that they can oxidize. So a deficiency in any one of those factors will cause your combustion to be a deficiency, or your combustion will suffer. So time, temperature, turbulence, 3 T's of combustion. Okay, I'll tell you what, let's just stop right there. We've pounded it pretty good today. So look at that homework assignment. We've got enough now